having me here. It's a pleasure. So maybe I should have chosen another topic because it's kind of far away from like topology, maybe. But the talk is supposed to be self-contained, and so please ask questions if things are not clear. Can you hear me? Actually, like
maybe a little bit louder.
Okay, perfect. Yeah, I'm going to start with the motivation. So for all this talk, G is a countable group, and X is one manifold for now. Okay, and the question I want to address is, well, like the overarching goal of dynamics of G is to classify all actions of G on X by orientation preserving homeomorphisms. Of X. Okay, and two caveats. Here, when I say classify, I mean like I'm considering actions up to conjugacy. That is, an action is a morphism of G into homeo of X. And I'm considering two actions to be the same if they're conjugate by an element of homeo of X. Okay? Second thing, I'm going to restrict to minimal actions to make all statements clearer. I mean, shorter. But when I say minimal, this means that all G orbits are dense in X. Yes? That's the object, the things I want to understand. Okay? Well, so this is a hard problem in general, but in some sense it's kind of solved if X is the circle. As a result of G's, later like kind of clarified by Matsumoto, that there exists Z, a standard Borel space, and a map from the space of minimal actions on the circle of G to Z, which is Borel also, such that the C fibers are exactly the conjugacy classes of minimal actions. Do you know what a standard Borel space is? Are you comfortable with that? Okay, it's a set with a sigma algebra, like say B, that is isomorphic measurably to the interval, say, with the Borel sets. Yes? Well,
or maybe you just want to say like the sigma algebra of a polar space. That's not.
Yeah. Is that okay for you? Sigma algebra of a complete sigma countable space. Okay, so the key word here is Borel. Like I can always choose if I'm working only set theoretically, I can choose Z to be like the set of all conjugacy classes, and yeah, well, it's done. But like when I say Borel, it means that, well, it's mathematically understandable. Like there is a complete invariant for minimal actions of these groups.
You don't really need the existence quantifier there, right? Because it's unique up to Borel as one standard.
Yeah. But the thing is, caveat that N is also a standard Borel space.
Okay.
But
right.
Yeah.
Right.
Sure. Absolutely. Okay then, so problem is that if X is R, the existence of C and Z depend on G. What?
If you start with a minimal action, you can adjoin any free group action to it.
What do you mean adjoin? Like?
Take free product with the
Yes, yes.
It acts. It's still minimal.
Yes?
How can you classify all the free group actions?
Bounded cohomology.
Oh, is that the invariant?
Yeah. The bounded Euler class. Now actually like the thing that will give problems here is exactly the free group. Like,
Does this have to be a faithful action? Like is G
no, not at all.
No? Okay.
That's why like in that sense like actions of free groups are like classifying actions of free groups is like a maximally complicated task in this setting.
I don't understand how we're answering the question.
Huh?
I don't understand how this answers the question.
Well, imagine if I told you this map was computable. Then that will answer the question in some sense.
Well, you didn't tell us what Z was in the first place.
No, I don't want to get into that. It's a bounded, like
It's answering the question in the sense of logic. Like you have a Borel reduction to something, like standard Borel space. Just take the sigma algebra of the reals or of Cantor space. You have right now.
Yeah.
But we can't take Z to be just a unit or
Well, yes, yeah, you can.
You can't.
Yeah, you can, but like it's not gonna make, it's not the best presentation for this problem maybe. Like if you do like measurable dynamics, like ergodic theory, you can also take the state space to be the interval usually, but that doesn't help depending on the map.
It doesn't help to call it Z either. You just, what you mean is that all standard Borel spaces are the same.
Yeah.
So you might as well not give it a name.
Okay, well.
Is that what you're saying? But
Yeah. Well,
So there's the countable and uncountable case.
yeah, but that's like a sort of thing.
Modular there.
Okay, is it better if I put the interval here?
yes.
Okay, then I'll do that.
But, okay, so now can you tell me again how that helps? In what sense is this a classification?
In the sense that you can check, like to check if two elements are in the same conjugacy class, you just have to compute C of these elements, of these actions. And the thing is that like being Borel is, I understand it as like being computable in some sense. It doesn't come from some axiom of choice.
What information do you have about the map C?
I don't want to get into that, but like it's explicit in some sense.
It's explicit?
Yeah,
Okay.
it's. I mean, it's hard to compute, like, but it's explicit. Okay. Well, I'm gonna give you some examples of groups G where like this works and others where this doesn't work. Okay, so there is such a map C. If G is abelian, or for instance, or finitely generated of sub-exponential growth, and well, the reason for this is that essentially that there's a result for these two things, by Hölder and Plante, Joseph Plante, that says that all of these actions, minimal actions of G, are by translations. Okay.
Sorry, when you say all these actions are by translations, you mean like all
Up to conjugacy.
up to conjugacy. Okay.
Yeah.
Whether or not G is abelian?
Finally generated. Huh?
Whether or not G is abelian, they're still by translation.
Yeah. I mean, you need sub-exponential growth. But, okay. Another example of a slightly more complicated group.
So
Yeah.
what is C now? What is C?
C is the map to the abilitization of G tensor R mod projectivization of this thing. Like each one of these actions, so these are all actions by translations, an action corresponds to a homomorphism of G to R. Yes? And I will identify two such homomorphisms when they're related by homomorphism at the target. And that's
I
this.
understand how to classify, but I don't understand what is the map C.
Ah.
Map C to 0, 1.
Okay, well, that'll take me a while to construct it explicitly. But it can be done. Like, I can't say more. Maybe I will say more afterwards. Okay.
Isn't it just the order structure of G?
I mean, you can build it out of left orders.
Left orders, yes.
Yeah, you can build it out of left orders. Yeah. Yeah, that's maybe a way. Okay. We'll take a group that's called the bounce-like solitar group, which is the group with this presentation. One bounce-like solitar group. More concretely, you can realize it as dyadic rationals, semi-direct Z, where you're multiplying by 2. This is the action. And there's a result by Rivas saying that all its minimal actions are affine. Yes? I mean, either they're given by this, they're conjugate to this thing, acting on the line. This guy acts by translations and this by homomorphisms. Or it acts by the abelianization of this guy.
So in this case, C is constant.
C.
There's non-faithful actions.
Yeah. There's a yeah, C is constant. Okay, yeah.
Assuming minimal actions.
Yeah. Okay. Okay. No. If G is F2, and I'll give you a construction to see why. So take a bi-infinite word of plus minus 1, and I'm gonna build an action of F2 generated, determined by two homeomorphisms. Yes? These are as follows. First one is called G, and it does not depend on omega. I'm going to put fixed points here. I'm going to declare these fixed points to be attracting and repelling alternately. Yes? H omega will have fixed points that intertwine with those of G. And the nature of these fixed points will depend on the signs of omega. Like for instance, if omega 0 is +1, I declare this guy to be an attracting fixed point. If omega 1 is -1, this guy is required to be a repelling fixed point. And so on. For instance, well, omega -1 is -1. Oh, sorry. Huh. Okay? I claim this can be done in such a way that the action you get is minimal. Okay? And also faithful. But the thing is that two actions obtained this way, phi omega and phi omega prime, are conjugate if and only if omega is the same as omega prime up to a shift of coordinates. Okay, so you can read like this word from the conjugacy class of phi omega. The thing is that there is no measurable way of selecting an orbit of the shift from each element here. Yeah. That's the reason why this fails for F2. Okay, so now so the question I want to answer now, which I will define some of the terms, and what follows is, what is the Borel complexity? It is a no. I haven't proved it, but the thing is, if you could do that, morally, you could choose in a measurable way an element from each orbit of the shift in this space. And that is not possible. Okay.
So you were saying something about the complexity of the equivalence relation given by
Yes.
the shift, right? And
Yes.
then, so you can formalize that.
I will. This is the, I mean, I'll write these terms and then I'll say what they are. What is the Borel complexity of conjugacy in the space of all minimal actions of a group, of given group G on the line? For this, I need to talk. I need language. Language of Borel equivalence relations. Okay. So, like in mathematics, there are many objects we want to classify that sit alongside each other nicely in a standard Borel space. They are parameterized by such. And you want to solve the classification problem, and examine the complexity of the classification problem given by an equivalence relation in this product, which I will assume is Borel, the subset. For instance, I don't know, geometric structures on a manifold or classes of dynamical systems. These are things you want to classify. But the examples I'm interested in are group actions. Okay, so if H, you take H a locally compact second countable group, and an action H on, well, I'll write here 0, 1, or Z by acting measurably. you get what Yash, an equivalence relation, right? You get an equivalence relation that Yash mentioned, which is the orbit equivalence relation. Then that I denote this way. Well, which is the set of all points related by the group action. This is Borel. The other relation I'm interested in, that pops up out of sun, is E0. The relation where you say two elements, two sequences of plus minus ones are the same if they differ by a shift. That is, well, there exists an n such that for any k, omega k plus n is omega prime of k. Okay. You want to compare, in some sense, the complexity of these classification problems in the same sense as you compare the complexity of computational problems. That for me is the motivation for these definitions I'm going to give now. So, take two E1 and E2 Borel equivalence relations on Z1 and Z2, standard Borel spaces that I'll denote them by different letters this time. Different symbols. I'll say E1 is Borel reducible to E2 if there exists a Borel map from Z1 to Z2. Such that X and Y are E1 related if and only if their images are E2 related. Yes? So this is saying if I can distinguish equivalence classes here, then I can do the same thing here. Okay, so this problem is harder than this one. If I can solve this, I can solve this. That's the main definition. And I'll say two relations are bireducible if the inequalities hold in both directions. Okay then. So the easiest kind of classification problems are the ones for which there is a complete invariant. These are called smooth. So E1 is smooth if it is reducible to the diagonal in a certain space. Yes, that was the case of minimal actions on the circle that I mentioned at the beginning of this talk. Next. E1 is essentially hyperfinite uniqueness.
Uniqueness of actions?
No. It means that no. It means exactly that there is a map from Z1 to Z whose fibers are exactly the E1 classes. Yes? Okay. So the relation is essentially hyperfinite if E1 is equivalent to somebody, I'm going to call it L, that can be written as an ascending union of relations where every Ln class is finite.
I mean, a silly way of saying that is that's just the equality equivalence relation.
Yeah, yeah. So that, so you can say. And I'll say this guy is essentially countable. If this is equivalent to a relation L.
Sorry, in the definition of smooth, you are specifying E1 is on Z itself. It's not like you could pick a different.
Oh, no. The Z is, well, take it W.
Okay, so that could be different than the.
Yeah, but again, it's
okay.
These are all the same up to cardinality. Like
Yeah.
these are the interval or n or finite sets. I mean, you can always take it to be the interval. Where every L class is countable. The people in model theory call this being classifiable by countable structures. And I emphasize that these two things are not the same. If I have a relation where every equivalence class is countable, it is not true that it is necessarily a union of subrelations with finite classes. The key word is Borel, because I need to measurably select things. Yes? Okay, so like you want to study this poset of bireducibility classes, and this poset looks a bit like this. You have smooth things. Up next, you have essentially hyperfinite things. And here, the only relation that is not smooth is E0. You have a bunch of things here, all under the umbrella of essentially countable things. And you have even more relations that are not essentially countable. Okay? So I want to question, where is conjugacy of minimal actions of G in this hierarchy? Okay, so the crash course is finished. I go back to dynamics. And it's a result of Brum, Matevon, well, what's the order? Rivas and Triestino. But it follows from work I'll cite afterwards that this relation of homeo of R acting on minimal actions is always essentially hyperfinite. So we saw that in general, that maybe depending on the group, if G is finally generated, sorry. In general, this relation is not necessarily here, but it's at least always here. It's a low.
Does your action have to be effective? Can it have a kernel?
Yeah.
It has to be effective?
No. It can have a kernel. Yeah, there are a bunch of groups with, like, no, I'm going to leave it there. Okay, so first question is,
So do you think it could be essentially hyperfinite but not hyperfinite? Like, is that?
No. The essentially is
Outside some null set, it's hyperfinite, right? That's what you mean.
no.
What do you mean?
What I said here is that it is reducible to a hyperfinite relation on the nose.
On the nose, okay.
Yeah, because like these relations have
Use the word essential.
essential. Okay. It's because of this. It's reducible to somebody who is hyperfinite. Because if you're hyperfinite, then you have each class has countably many elements. And that is not true for conjugacy of these big groups, because these are, I mean, non-discrete things. Okay. So first theorem. We don't know if this is true if by dropping finitely generated. I suspect it's true. But the thing is that this proof is really neat. Like it comes from an observational detail now. But thing is, this guy is always, let me call this rep min. This guy is always essentially countable. I won't tell you about always, independent of if G is finitely generated or not. And I won't say anything about the proof, but I will say something about this proof because of propaganda reasons.
Always essentially countable.
Ah, yes, it's always. Thank you. Okay, so second intermezzo. I'll tell you why this is true. Okay. So the note by psi translation, conjugacy by translations. Okay, and there's a theorem by Deroin, Klepsin, Navas, and Parwani that tells you that whenever G is finitely generated, there exists a subspace of minimal actions. People call it the harmonic subspace, which is locally compact and psi invariant, such that there exists also a map, well, call it R, from all minimal actions to W with phi1 satisfying that phi2 are conjugate if and only if their images are translates of each other. Okay. It's saying that the classification problem reduces to a real flow in a locally compact space. And a real flow, well, we use that as a black box, but these relations are always essentially hyperfinite. But in general, if G is not finitely generated, there is no such space. I think we have proof of that. And it raises the question of characterizing, making explicit these spaces for your favorite finitely generated group. That can be done, but it's hard in general. Okay, so. So some further results address this question of when is this relation smooth?
So this R is going to be some sort of like projection map.
Yeah, it's a retraction.
Retraction, yeah.
They call it harmonic retraction. Question is, when is this guy smooth? Okay, explicitly define C as a class of people such that this relation is smooth. For instance, we have no amenable group. It is not in C. Amenable left orderable group. The thing is that what we show now is that this class is big. Like, I'd like to know if actually all amenable groups are in C. We prove some closure properties of this class. First thing is, if G is finitely generated, and G contains a normal subgroup such that both the quotient and the kernel are in C, then G is in C. Yes. And a refined version of this lemma gives like a lot of new examples of groups with, that emit that are in C, for instance. A cute example is all these bounds like solitar groups. Finitely generated solvable groups. And what we call Reth products of groups. Two finitely generated groups in C. So I have to define this, right? This is the semi-direct product of G copies of H So we direct G, where the action of G on this countable sum is by the permuting coordinates. So these are groups with like a rich array of actions on the line. Well, they are classifiable in some sense, even though like getting your hands on the concrete invariant is difficult. Okay, so we know F is in C. Thompson's F. This comes from an explicit classification of all its actions on the line. What we prove also is that any finitely generated subgroup of piecewise affine homeomorphisms is in C. I'd like to emphasize that if I give you a group of piecewise affine homeomorphisms, it is not true that all its actions are by piecewise affine homomorphisms. And the idea is to show that all these actions, while not factoring through this group, they are all governed by this initial action. Okay. Yes.
Martin, is this true as you stated, or do we have to, because I think in the paper we wrote this fragmentable group, there were some conditions on G.
Okay, no, maybe the problem is with what is piecewise affine? Or
The groups of germs, there is this thing that you can write G as a composition of something which has compact support, bounded support, and on one side, on the other side, say G is fragmentable.
No, this is true. I mean,
it's true in general.
This is absolute general. This is part of the work.
That you did with.
Yeah. Yeah. No. Yeah, you need more things, I think. Than.
You allow the infinite remain breakpoints?
Yeah. That's it. I mean, it works for piecewise projective stuff too. Okay, and the final thing, which is actually like this is due to Nicolás and Joaquín. They found it before I was involved in this. Is that this question of whether all amenable groups are in C it can be extremely difficult to decide. Like we found an example of a group G bar that is finitely generated such that G bar is not in C. And G bar is amenable if and only if F is amenable. Okay. So on the one side, if you prove that all amenable groups are in C, then you've proved that F is non-amenable. If not, then I mean, if C does not contain, if there is an amenable group acting on the line that is not in C, then you have to find essentially new ways to produce groups acting on the line. That's a hard thing in general.
You find this tilde PPR?
No, it's not a subgroup.
So in the homeomorphism group of R.
What?
So here is in this G.
Wait. Yes? I didn't get the question.
Tilde lies in PFR.
No. Because it would contradict this.
You are saying no. So G tilde is in the homeomorphism group?
Of R. Yeah, I mean, there's a dumb reason why a group. I mean, if G tilde did not act on the line, then it'd be in C, by there are no actions to classify, then you.
We can take F direct sum Z mod to Z.
Yeah.
I don't understand your answer. So where do you find this G tilde?
It's like a homeomorphism group of a solenoid. I mean, of a what you call a matchbox manifold. It's this like it's a space which is locally transversally Cantor and times a line. Yes, and the local maps are like F-like maps, but you have to do several things with this. But this is like the basic object. Game. You could talk about proofs, but I'm not feeling very well, so I'll leave it here. Thank you.
Thank you. Questions?
If you don't insist on your actions being minimal, but then you do consider them up to semi-conjugacy, does anything change?
No.
It's all the same.
I mean, yeah. Actually, like it's even not clear to me a priori that semi-conjugacy is like a Borel thing inside actions. Like because this is like conjugacy is given by a group action, a polished group action. Semi-conjugacy is a weird thing, like, but it is in the end. It is a Borel thing. I mean, you can define C as semi-conjugacy.
Well, thank you so much.